So now that we've talked a little bit about alkyl halides, we're going to spend a little bit of time talking about how they are made. And in order to do this, we need to take a deeper look at radicals. Now, just a quick review. What is a radical? Should answer that in your head before I write it down. Something with an unpaired electron, like, for example, a chlorine radical, or, if we wanted to put it in terms of organic stuff, a carbon radical. So if this is not familiar, you need to go back and look at our previous unit where I highlighted radicals. So let's dive a little bit deeper. What is the hybridization of a radical? Now, this is a little tricky and complex to talk about, but let's compare it to some things that we know the hybridization of. So the hybridization of a carbocation, that carbon has three regions of density around it, is sp2. Let's go to the other extreme and look at a carbanion. Well, how many regions of density are around that carbon with that lone pair? There's three regions of density, so it's sp3 hybridized. A radical is somewhere in between in terms of its hybridization. It's closer to sp2, but it's really not either one of those hybridizations. And there's something important to note, and this will come into play a little bit later, is that um, radicals cannot be chiral. So even though you might start with a chiral organohalide, once that halogen is gone to make a radical, the radical itself cannot be chiral. Now let's talk about the stability of radicals. They're very reactive, but they seem to follow an order of stability very similar to carbocations. And the reason for that is like carbocations are stabilized through hyperconjugation. So the order of stability, we'll start with methyl radicals. Those are the least stable. And then primary radicals. And we have secondary. And then we have tertiary. Now I'm going to add some of this list. I talked about this with the stability of carbocations. We also see that radicals can be resonance stabilized. And in fact, those that can be resonance stabilized are a lot more stable than tertiary, which really wasn't the case with carbocations, but allylic radicals can be stabilized by resonance. I'm going to add one more to this list. I didn't highlight it in carbocations, but it's a kind of special type of allylic carbocation. And we call these benzylic carbocations. Benzylic, so little crash course here. This six-membered ring with those three double bonds in it, we call that benzene. And the first carbon outside of benzene, highlight it right here, is known as the benzylic carbon. And so this is a benzylic radical. Now, the reason these types of radicals, allylic and benzylic, are more stable is because they are resonance stabilized. So let's draw a resonance form for the allylic carbocation. Now, how do we get there? Well, because we're dealing with radicals, we're going to use these little half arrows. Now, a couple of important things to note about radicals that are somewhat common mistakes I see students make is you don't want to make a vinylic radical. Okay, that's never going to happen. Now they call this vinylic because the radical is on the double bond. That's much different than allylic. Make sure you know the difference between the two. And then another important thing is that there are no rearrangements at all with radicals. You can't go from a less stable radical to a more stable. There's no way to move atoms around properly to make a more stable radical. All right, so let's talk a little bit about the reactions of radicals and organohalides. So I highlighted this in an earlier unit, but we looked at a reaction where we took methane and reacted it with chlorine and light, and that replaced a chlorine, I'm sorry, a hydrogen with a chlorine. And then we looked at the mechanism for that. So review that real quick. But we can keep on going. I didn't highlight this, but if we had more chlorine, we could replace another hydrogen, and then it could keep on going, replace a third hydrogen, and then finally could end up replacing all of them. Now, before I start going deeper into the reactions to make organohalides, I would need to do a comparison. And in down the road, you might be wondering, well, why are you only using these types of halides? Why aren't we using the other ones? So let's just look at a comparison. I'm going to use a generic halogen here. And we're going to compare fluorine to chlorine to bromine to iodine. And we're going to look at the delta H of these reactions, which is pretty close to what delta G is. We're not changing entropy much. So, when we talk about delta H and delta G, um, we can assume that it's also a measure of spontaneity. Now, for fluorine, it's very exothermic. So negative 431 kilojoules per mole. Chlorine is negative 104, bromine is negative 33, and iodine is plus 55. Now, if we look at the value of those numbers, fluorine is too impractical for us to use in a lab. This is way too exothermic. If we try to do that, it just would literally blow up in our faces. Not good at all. And if you look at iodine, that reaction won't be spontaneous. So using fluorine or iodine to do these reactions is impractical because one's way too reactive and the other one's not reactive enough. So the sweet spot seems to be here with chlorine and bromine. So you will see reactions using those. Now let's take a look at, well, sorry, let me just back up. Notice here we used methane and replaced a hydrogen with a halogen. Okay, that gets kind of boring after a while. Let's look at a reaction here. We're going to take propane and react it with chlorine and light. Now you'll notice that there are two positions here. I could replace one of those hydrogens, or I could replace one of those. Which one do you think will be the predominant location to replace? And you want to think about, well, what would give me the more stable intermediate, the more stable radical? So what we call the major product here would put the chlorine there because that comes from the more stable secondary radical. Now we do get some of the primary halide. And the ratio is about 60% to 40%. So secondary is favored, but not by much. In chemistry terms, we say that that's not very selective. We like reactions that are very, very selective because it just cuts down on our time and money and effort to have to purify it. So um, by having this, if our intended product was to put the chlorine in the middle carbon, like only getting 60% of that is a huge waste of a lot of resources. Now, by changing up the halogen, let's do the same reaction, but this time use bromine. Again, we'll see a similar product distribution where we'll have some secondary and some primary, but 97% of the product is the secondary one and about 3% is the primary one. So we would say that bromine halogenation is a lot more selective. And that's typically what we will use in chemistry is to make alkyl bromides. Not that we can't make alkyl chlorides, but we'll do them in other ways. So let's look at an example. And this is a type of question you're going to see on homework and exams. So you'd see this. I draw the reactants and ask you for the major product. And what I mean by the major product is what is the one you're going to get the most of? And I very rarely will I ask you for all of the products. So when you read the instructions, it'll say, draw the major product. I'm looking for one specific product. So you need to look at the hydrocarbon here and look at the different, for radical halogenation, you want to ask yourself what forms the more stable radical, because you got primary all around here. That's not great. You got a secondary here. That's a little bit better, but you have a tertiary one here that will form a tertiary radical. That's the more stable intermediate. And so that is where your bromine will end up. All right, let's look at another example. So again, what is going to be the major product? So you want to identify primary versus secondary versus tertiary. And this carbon right here is tertiary. But not only that, what else do you notice about it? It's chiral. So what role does that play in how the product looks? Well, let's just kind of look at, a small part of the mechanism for this. So bromine radical gets formed here. And so we're going to extract this hydrogen to make the tertiary radical. Now, do you remember what I said in the last video about radicals and chirality? We started with something that was chiral. and radicals cannot be chiral. So when this combines with bromine to form our product, we're going to get a product at the end that does have a stereocenter now, but it's not R, it's not S, it's a racemic mixture. And do you remember what that means? An exact 50-50 mixture of enantiomers.